So now that we have a working processor, we can take code, binary codes, zeros and ones, a set of instructions of zeros and ones, and do things like read a memory location and store it into one of the processor's registers. We could take data in one of the processor's registers and write it back to a memory location. We could take two registers and add their results together and store that in a third register. So these are things that the processor can do, but what we'd like to do is we'd like to be able to write computer programs and somehow have the computer processor take what we write. I mean, in other words, we wouldn't want to write stuff like take the contents of this register, move it into the processor, and then the next step, take the contents of another register, move it into the processor. We'd like to be able to do something like this. We'd like to be able to say A equals B plus C, semicolon, and have something interpret that to mean, obviously, we're going to take the contents of memory location B, grab that, contents of memory location C, grab that. In a third step, add those two results together, and then in a fourth step, write the result back to memory location A. So if we run this through, let's say, a C compiler, let's say this was C code, ran this through a C or C++ compiler. It's a little bit different for Java, but if you ran code like this is like legitimate C code, through a C++ compiler, the output would be what's sometimes referred to as machine code. So this is C or C++. And machine code would come out. Which of course is zeros and ones. The only thing that can run on the processor is zeros and ones. So a bunch of zeros and ones, 0, 0, 1, 0. That might mean load the contents of, this could be a load operation. We're taking memory and putting it into a register. So this might mean a load. Then maybe memory location B could be, depending on our architecture, sometimes we had 2 registers, sometimes we had 3 in each instruction. So maybe register, let's say we wanted to load something into register 3, that would mean a 3, that's the register it's being loaded into. And then maybe the location could be, the next set of bits could be the memory location we're getting something from. Then the next instruction, which would also be a load instruction, would end up having the same first, so many bits we dedicate to each of the different types of instructions we have. So this might be another 0, 0, 1, 0. This would mean if 2 was a load operation. We can make up anything we want for our architecture. And then we might say load into register 4 the contents of C, and then this would be the address of C. And then the next step would be to add B and C together. So maybe the add operation, so whatever we're putting here decodes into some piece of the hardware getting electricity applied to it, and that thing takes, that piece of hardware has electricity flow through it. So maybe an add operation would be a different code here. It could be 1, 0, 1, 0, and maybe this means add. And then we add, maybe we store the results into register 5, 0, 1, 0, 1. The contents of register 2 and the contents of register 4 get added together and put into 5, right? So, and then the final step might be a store, to store back, and that would be another different code. Let's say store was this one. That means store. I'm just making this up. But we're storing the contents of register 5 into a memory location 4A. So for a particular architecture, a line of C code like this would go through a C compiler and actually have this as machine code, right? Now you can imagine this could get very, if you read this with your eyes, you can't really tell what's going on. So considering the fact that the first several sets of bits, if you want to have more instructions, you got to add more bits. But maybe the first set of bits tells you what type of instruction it is. And then depending on the type of instruction will tell you what comes after it. Maybe there's registers here, maybe there's memory locations. For an add, it would be a collection of registers. For a store, it would be a register and a value, a location you're storing to. So wouldn't it be nicer if we could write this code out in looking more like English, but in a step-by-step? So there's a language called assembler language, which is, it's really like a sister language to machine language. There's a one-to-one map for every machine instruction. There's an assembler instruction. But assembler looks a little bit more like English. So it's a little bit more readable, and it might look something like this. I'm just going to make up assembler, depending on what processor will determine what assembler language there is. But it might look something like this. Load into register 2 the contents of memory location B. And this line actually could be decoded. And what I mean by decoded, just read these bits, the word load shows up. Read these bits, the register 3 shows up. And then read this location, and that's some location that the compiler designates to be equivalent to C. Then this instruction could be add. Add, store the results into register 5, the contents of register 2 and register 3. Take what's in register 2, register 3, run them through the electronic adder, and have the results get routed into register 5. And then the last instruction, this is the machine instruction, and this is the corresponding assembler instruction, would be store. For some reason they drop off the E. Kind of chop it at 4 letters. Store register 5 into memory location A. So effectively what's happening is you're writing a line of C or C++ code, and this is, this is good for you to work with, because you kind of know what you're doing here. Then when you're finally done, you run it through a compiler, a C++ compiler. The C++ compiler reads this code and generates, this is the executable file. It generates corresponding machine codes that will run on the particular processor you want to run that on at the moment. If for some reason, this was very popular back in the 1960s or 70s, a lot of debugging was done on this stuff. They didn't debug here and then recompile it. They would debug this code, and some people even wrote assembler code, machine code by hand. But a human being's not going to be expected to go, oh, I see that 1 was supposed to be a 0, and that's the problem. So what you can do is run it through a translator that translates this into direct line by lines, and this looks a little more like English. Now we can kind of follow what's going on. So a lot of times you hear people say compilers take high-level language code like C and C++ or Java, and they generate assembler language code. That's not really true. They generate machine code. Assembler is just a program that reads machine codes and converts it into somewhat English-looking line-for-line code. Okay. So now the question is, can we take, all the things we do in our high-level languages, can we generate a corresponding machine code to run that program? So forgetting about the machine code, maybe I'll just skip this and write it from now on as assembler, because it looks a little more like English, something we can understand. So suppose we had code that went like this. We had C or C++ code that said like, if A is greater than B, then we say B equals C plus 2. Else C equals 0. But for whatever reason, that was our code. How could we do a one-to-one? The compiler would have to take this and generate the corresponding machine code, but I'm not going to write out the machine code, I'll write out the assembler code. So what would be the corresponding assembler for this? So we've already talked about creating a processor, and our processor, I think the processor we did was unbelievably simple. Obviously, real processors do more than what we went over, but we were able to take two numbers and add them together. We were able to take a number and just let it pass through, which sounded like a meaningless step, but we'll get to in a second why we needed that. So that basically took as input a register, and then just one time unit later, the results just got copied down. I think we had another another CPU operation that took a register and checked if it was a 0 or not. And all we did there was we took all the bits, flipped them over, and then ANDed them all together, and if they were all originally zeros, we got a 1. So that was a root. So what that basically means is we now have an assembler instruction where we can make up, since this is an official assembler, we could say, you know, is 0 register 2? Well, no. If we could give a register and then ask, is it 0, and then we'd have to actually, if it's 0 or not, we'd have to actually do something with it. But another piece of hardware we could do, if we wanted to have if we had a register and it had a bunch of zeros and ones, if we wanted to know, is this a negative number or not, could we come up with a piece of hardware that could do that? And that would be pretty straightforward. If we use the 2's complement, the higher order bit determines if it's positive or negative, right? So if we ever wanted to know, is this number positive or negative, we just let the higher order bit come through. 1 would be positive, 2 would be negative. If we needed to flip, we just run it through a NAND gate. I'm sorry, NOT gate. So how can we do logic? So we pretty much know that with a processor, we can do stuff like read from memory, perform some math, write back to memory. Now the question is, can we do like conditional, if A is greater than B, do this, and if B is not, if the other is true, then go here. And if we do this, after we're done doing this, we should skip this one, right? That's what we want to happen. So how can we do that? So how can we implement an if A is greater than B? So all if statements in all your programming courses, this resolves eventually to a true or a false, right? You could have a big clumsy statement, but eventually it's either at the end true or false. So how can we check, is A greater than B? Well, so we'd ask ourselves, if we put A and B into registers, well, it looks like we're going to need A and B, so we're going to end up doing load. And I'm just randomly picking register numbers out of my head. I think in our processor we had 16 registers, but they could go as high as 32. So load register 6 with A, load register 9 with B. Okay, so now we went out to memory and we grabbed these two numbers. Is there some piece of hardware where we can now figure out, is this true or false? And if true, we need to go to here, and if false, we need to go to here. If true, we need to go to here and skip here, and if false, we need to skip here and do that. Okay, so if you had two registers, could you come up with a piece of hardware that tells you whether or not the first one is higher than the second one? I guess you could go through the high order bits, and bit by bit, and the first one to have a 0 is the lower one. Would that be true? If it was 5 and 3, if we put a point, if we just went through each bit, We'd have to come up with a piece of hardware that takes these two, and as long as they match, go to the next one. But if they don't match, whichever, then that means one's a 1 and one's a 0. Whichever one is the 1, that's the higher number. That would be true, but how would we draw it? How can we do that? We would have to take the two inputs and say, this number and this number, if they don't equal each other, we could use an exclusive OR. If they don't equal each other, well, so, okay, so we'd have to come up with something. If they did equal each other, then we want electricity to go through the next two, bring those two out, and if they equal each other, go back. So we could kind of do a rippling. We could eventually come up with a piece of hardware that takes as input two registers, and then will tell you, and has one output that's it's a 1 if this one's higher than this one, and a 0 otherwise. But without that, because then you'd be making a big piece of hardware just for this one computation, is A greater than B. And we could end up having a more complicated one. So if we didn't have a piece of hardware like that, could we still, with what we do have, adding and subtracting and then checking if a number's negative or not, could we do that? What we could do is we could say, let's subtract A from B, and if the result is negative, if we subtract A from B, if the result is negative, that means this was true, right? So we could say subtract, and put it in register 12, subtract A from B. Now, if register 12 is negative, and if we had a piece of hardware that just checked the higher order bit, that's an easy piece of hardware to make, so then we'll have a corresponding assembler instruction for it. We could then say branch negative. Now, what I'm doing is I'm kind of taking liberty. I'm making up instructions as we need them. What we don't want to do is make up an instruction that kind of does too much magic. If we can only make up an instruction if there's a simple piece of hardware that can do it. Then we can say, all right, let's add that hardware to the processor. So I can have a simple branch not 0. Branch meaning if check the high order bit of register 12, so branch not 0, 12, register 12. Check the high order bit, and if the high order bit is a 1, then we're doing what's called a branch, and we'll just go over this in a second. And I'll put a label here, label 1, let's say. So I'm taking the results of register 12, and if it's negative, meaning the higher order bit is on, my next instruction will not be right after. Right now, all the instructions just go one after another. But if we had a mechanism where we can say jump to some other location, now we have to think of a corresponding piece of hardware, because that kind of sounds a little magical. We're just going to jump. If a wire is on, then jump somewhere. But what we're basically going to do is if this register contains a negative number, we're going to jump to this label, and I'll write the label down here in a second. Now, what would we do if it's not true? We would say, load register 9, nope, I use 9, register 10 with C, add to register 10 the number 2, store into store register 10 into B, memory location B. Okay, so this line is showing up here. This part is pretty much this whole piece. Oh wait, I haven't covered the closed paren yet. I gotta cover the, yeah, leave that. So now, I'm gonna put a label down here called label 1. Semicolon. This is where we would go to if this came out to be false. We would come down to here. And what is down here? Oh what? Okay, we could just say store into locations store a number 0 into location C. Now the problem is we don't want to, if A is greater than B, and we go executing these 3 lines, we don't want to execute this one. So we need to, when we get to here, jump around this one. So we would then need a branch instruction, which means unconditionally just jump somewhere else. So we'll say branch to label 2. And then I'll put label 2 here. And this could be the end of our program. And means stop processing, there's no more instructions. So now the question is, so this looks a little magic-y, this branching stuff. But could we come up with a piece of hardware that could branch? Based on a condition, just have a wire that's either true or false. If the wire is true, then the very next instruction is not the one right after it, it's go down to the label and start executing from here. Would that be a hard thing to do? So, let's first talk about how instructions are actually run. Instructions have, I'm going to erase this, but just remember, really the only thing that's kind of new to us is this idea of branching. Because right now, basically, the way we said our processor worked was we have machine codes. This is the assembler-looking version of the machine codes, but these are all just a series of zeros and ones. And we had one of our registers we called the program counter. That's the pointer to the next instruction. And every time we ran an instruction, one of the things we would do is add, however big the instruction sizes are, add that to the pointer, so we go to the next one. So every time we complete an instruction, we add one more instruction size to it, and it just keeps going down. So what we want to do is we want to be able to say the part where we want to add a different number. Now if the compiler knows exactly the spot we want to go to, it knows exactly how many instructions later it is, and the way the compiler would do that is just remember where it needs to go to, if the else is. Then instead of adding one more instruction, where is it here? Instead of adding one more instruction to get to this one for the next one, it'll calculate 1, 2, 3, 4, 5, and it'll add 5 to get us there. So there's kind of some behind the scenes stuff going on for each instruction. Like right now we're just kind of accepting that this instruction runs. Right? Somehow the hardware decoded the ones and zeros, the instruction ran, the processor gave it a certain amount of time, and then obviously we went to the next instruction. So there's some kind of behind the scenes stuff going on per instruction. And one of those behind the scenes steps is we calculate where the next instruction is, and this thing is just going to these branches, this branch if negative, and then branch no matter what. These instructions will feed into one of those steps. So I just want to talk about those steps. Every time any instruction is run, and I think we had, when we were talking about some hardware, we had a thing called a clock, which basically, let's say, I think we want to keep this simple. We'll have a clock that has 4 wires coming out of it. And what the clock is doing is it's running autonomously, and basically electricity applies to this wire. Then a fraction of a second later, electricity applies to only this wire, not these 3. Then a fraction of a second later, the 3rd wire. Then some fraction of a second later, the 4th one. Then it just keeps going 0, 1, 2, 3, 0, 1, 2, 3. Just doing electricity, electricity, electricity. Kind of like sparks on a car. You know, like the rotor keeps saying, you have 8 cylinders, it sends 1 spark to each of them over and over. So the clock on a processor is kind of like the, what's it called, the rotor, right? The thing that sends the sparks out to the spark plugs. So it's basically firing here, piston. Then, what's that? Piston. Well, yeah, it's sending them out to, and the spark makes the piston go. But the thing that's distributing This is distributing electricity here, then here, then here, then here, then here, you know, over and over and over. So, and this runs just based on electricity coming in. One of the components we made was the thing, if you supply electricity to it, it will just, based on the speed of the gates inside, will just go electricity, electricity like this, just over and over and over. So, and we could, I think we talked about how we could slow this down if we wanted to, so we could kind of control the speed of the clock. But there's 4 steps to getting each instruction running. There's a fetch step. So now we're just looking at one instruction, like load register 1 with memory location A. Just an instruction like that. There's really, it depends on your architecture, but we're going to keep it simple. We'll have 4 steps. So 1 is to fetch the instruction. Number 2 is to decode it. The 3rd step will be to execute it. And the 4th step will be to store any results back. So basically, what do we mean when we say fetch the instruction? So okay, let me do this. Load A, and then I'll say load register 2 with B, and then add register to register 3, add register 1 and register 2, and then the 4th one, store register 3 back to C. Let's say we have these 4 lines again. To execute, let's say we just finished executing the first line. What steps are now needed to execute the second line? Load register 2 with B. So our program counter is pointing to, now remember, it's actually pointing to machine code, the zeros and ones. I'm just writing this out so we can kind of see it. But this is, these machine codes, these sets of zeros and ones are in our memory. One of our registers is pointing to this instruction. What we now have to do, now that this instruction has finished, what we now have to do is we have to execute this next instruction. So what do? First thing we do is we add one instruction size to the program counter. So we have a program counter. That's a particular register which its contents is the address of this instruction. Now one thing we have to do is we have to fetch the next instruction. So that means step 1, add to the program counter, add 1 unit, which means the next instruction. And that way we can then capture these zeros and ones in an instruction register. Then the next step would be to figure out what is the instruction doing. It could be doing an add. It could, so the first step is to get the instruction. And that involves adding something to the program counter to get to the next instruction. And then latching all of the bits for it into the instruction register. Now what we want to do is say, okay, now that we have the next instruction, what does it do? It could be doing an add, it could be doing a store, it could be doing a load, it could be doing a branch. So we let the electricity of it flow through the hardware to figure out what it is it's doing. That second step is called the decoding step, where there's no thinking going on, the processor doesn't think. The electricity is floating through, so we eventually, the bit that turns on the, like if it happens to be a load instruction, the bit that turns on the adder will be off, the bit that's doing storing will be off. The bit that's doing loading, meaning opening up our register, our set of registers, that will open up. So we let the bits flow through, and that's the decoding step. Now at this point, if there is a piece of hardware, like if it was an add instruction, if there is a piece of hardware that now has to begin some process. For example, we talked about the full adder, right? If you remember, the full adder was a series of adders hooked up to each other where the results of one was going into the next one. And it would do, you know, a rippling effect like this. Once we figured out that after the decoding step that we are applying electricity to the adder, if we're applying electricity to the adder, that means we have to take the two registers and this flow has to go through. So that would be the step where the instruction is actually now being executed. And then the results of it come out of the bottom of the ALU into storage. And if there's anything of the results that has to be written back to memory, that would be obviously the final step where we're writing results back. Now, if you wanted to, obviously we could make more steps come out of this, and we could make our clock have more wires coming out of it. If we wanted to make 6 steps for the instruction, we could do that. But I'm just trying to keep it simple right now, that every instruction has, I don't think I've ever seen an architecture that had 3 steps. So they have at least these 4 steps, and then maybe even some more if you wanted to make the instructions be more robust, that they can do more stuff. But you could argue that that might not speed things up, because if the instructions can do more stuff, then the decoding step might take longer, because you have more equipment on your processor. So you might have to let more time to decode the instruction if you had more complicated instructions. But more complicated instructions might get some work done quicker. But you can't always argue that the more complicated you make the processor, the quicker any random program could run. Simple programs might take a really long time because your processor is built to handle very complicated instructions, and therefore you might have had to slow the clock down to handle those complicated instructions, and maybe the users of your processor aren't utilizing these complicated instructions. They're doing simple things like adding A plus B equals C, and they don't need all your complicated stuff. So that's a trade-off between well, I'll get to that in a second, RISC and CISC architectures. But so anyway, right now, the 4 steps that are involved in executing one instruction, like running this one instruction, takes 4 steps. The fetching the next instruction, decoding the instruction now that you've got it. Now that it's been decoded, we know which parts of the processor have to take some kind of action. So the action is then taken, and by the end of the action being taken, we may or may not have results that need to be stored back. So if the clock just says do a fetch, a decode, allow enough time for a fetch, allow enough time for a decode, allow enough time for an execute, allow enough time for a store, then a fetch, and just keep doing this over and over and over. The clock runs at a constant speed. It's most likely that the execute step will take the longest amount of time. For example, if you did an add, we need enough time for the electricity to ripple through to get our result. The decoding step probably doesn't take that much time, because once you apply the instruction to the instruction register, the electricity flows out, and in almost no time we've figured out what piece of hardware needs to do something. So it's the execute step that takes a lot of time. And so some consideration is given to taking the execute step and breaking it into 2 steps. So now we can make the clock cycles go faster, but just the execute part takes 2 units, and these parts take much less time. So for example, not that there's a processor this slow, but let's say an execute, the hardest piece of hardware that we execute could take 4, I mean this would be milliseconds, but 4 units of time to do. Let's say this takes 2 units of time to do. A decode only takes 1 unit of time, and a store could take 2 units of time. But your worst case scenario on an execute, let's say it was some big math operation, takes 4 units of time. We would have to set the clock speed to allow 4 units of time for all of these steps, because one of them needs 4 units of time. So to go through a whole instruction would actually take 16 milliseconds, or whatever these numbers are, when really all we really needed was 2 plus 1 plus 4 plus 2. 9. But because we broke these into 4 separate steps, it ends up taking 16. So some consideration might be broken up to, if you could do an execute 1 and an execute 2. 2 and 2? Right, and give 2, so of all the mathematical operations you can do, you'd have to partition them into a first half and a second half. But if you can make that partition in such a way that the maximum of all your components would ever take is 2 and 2, then we could have a clock, have the clock have five things coming out. Do this step, then do this step, then do this step, then do this, then do this, and do that over and over. And then we can make the clock, since we control the speed of the clock, we can make the clock now, the clock has to be as slow as the slowest step. So now the clock can go every 2 milliseconds each of the steps. And now an entire instruction could take 1, 3, 5, 7, 9. Yeah, this would be the perfect speed. Oh no, I'm sorry. 2, 4, 6, 8, 10. It would take 10. Because we'd have to give the decode step 2 seconds because everything gets the same amount of time. So yeah, so now we went from 16 to 10. So now what we're doing is we're starting to complicate the components of our ALU to get better results. And then sometimes, maybe whatever the piece of hardware that took 4 units, it's not every mathematical operation takes 4 units of time, but maybe there's one complicated thing we added, and that slowed our whole system down. It might be better to just get rid of that one. And then maybe we could have just made this 2 in the first place. So, like, I'll give you an example of a very simple example of a processor. The one we talked about when we were talking about processors can only add 2 numbers together, right? So, for example, if we had A equals B plus C, our processor would do the standard load register 3 with B, load register 4 with C, add register 6 with register 3, register 4, and then store register 6 into A. Now what if we did this? A plus B plus C plus D, right? We could do that in C and C++. If our architecture only allows addition of 2 numbers, doesn't allow 3 numbers, this would compile into load register 9 with a D, and then add, because we'd have to add B and C as one step, then add that result, add D to that, and store that back. And then we could say add, oh, we shouldn't have done that. We're not storing anything. Add register 6, it's all close to register 6, R6 to R9. R6 plus R9, put the results in 6, and then store R6 to A. Okay, so that's because our architecture only allows 2 at a time. Suppose we had an architecture that allowed 3 numbers. I mean, we would do one of those ripple adders, but we'd have to figure out a way to take 3 inputs and add them all together. Let's say we had a piece of hardware that did that. It would make the assembler instructions simpler. We could say load R3B, load R4C, load R5D, and then add to R9, R3, R4, and R5. We can write the assembler if we have a piece of hardware that can do it, right? Then it becomes one line of assembly. And then store R9 into A. So less instructions because we have more complicated hardware. But the problem is that piece of hardware, I mean, we could, as a homework assignment, we could come up with something that takes 3 registers and adds the results together. But you can imagine it would take longer time to do. Since it takes longer time, that execute step would have to be given more time. And therefore, we're slowing everything down. Now the fetching and the decoding and the storing steps are given unnecessarily more time because we've added a new piece of complicated hardware in. But then we could try that trick to maybe cut it into 2 steps, and then we have to take the execute step and cut it into 2 parts, and then we'll get a better result. So there's kind of a trade-off. You can go read about this on Google, but they have reduced instruction set computing. That's where you keep your instructions simple. And this is like a good example. We can only add 2 numbers at a time. If you want to add 3 or 10 numbers, you have to do them one by one, sequentially. And then that's versus complex instruction set computing. That's where you come up with these really nice pieces of hardware that perform hopefully commonly asked steps, but they take longer to do, therefore you have to slow down your clock cycle. So there's really no right answer. What it's going to come down to is who's going to use this and what programs are they going to do. If somebody had some real simple program, A plus B equals C, and you have this really big piece of hardware that can add 12 numbers together at once, they're not using it, and your processor has to run slower because they may use it, even though they're not using it. So it really depends on who's using it. Would determine which architecture you want to use. Okay, so then the step we were talking about before, we had a step where, because we wanted to be able to do branching logic. So if A is greater than B, we want to ask ourselves, can we come up with a piece of hardware that can say, if a condition is true, the next instruction should be down here, not the following instruction. Can we come up with a mechanism for that? And the mechanism we do that is on that fetch the fetch step. The fetch step updates the pointer to the next instruction. Now what we would do is just update it to what we were calling a label. And all the label ends up being is the compiler will calculate the distance between that label and the instruction that's doing the branching and just add that amount to it. And then that's how we can do something like this. Then there's theoretical arguments. If you take a class, I don't know if we have a class like this, but the algorithms design class, maybe towards the end of the class, they start getting into theoretical arguments about what does it mean to be computing. But basically, if you could read from memory and write to memory and then do branching logic, you can write any program in the world. That's all the functionality we'd ever need. But that's kind of a side argument. But once we have a processor that can handle branching, so it doesn't just blindly go instruction one after the other, it can actually make a decision. I want to go to this instruction, not that instruction, based on a condition. Once we do that, and we have the ability to read and write from memory, we can pretty much write, the processor can pretty much handle any computation you'd ever want to do. And the programming language should be able to allow you to perform any computation you want. So then we can write a compiler that goes from C code to machine code. And then just one last side topic. It's not really a computer architecture topic, but when languages like C and C++ get compiled, when they go through a compiler, the output of the compiler is machine code. Which only runs on the compiler. Oh, sorry. Only runs on the processor. The compiler was made for. Does that make sense? That the so what a compiler takes as input is legitimate C or C++ code. What its output is, it already knows how the hardware was built for the particular processor you're compiling for. So like if you use on our system here, we use the GNU compiler. So say C++ my file dot CPP and hit enter, as long as there's no bugs, you're going to create a file called myfile.exe. And that's the zeros and ones that will only run on the machine that this compiler was built for. If you then took this file and sent it to an Apple machine, let's say you did this on a Windows, a Dell, a Motorola processor, and then you took this file and emailed it over to your Apple machine and tried to run it, it's going to be garbage, because it wasn't meant for that machine. So what the creators of Java, when Java came out, this is like pretty annoying. Every machine, if you write a piece of code and want to run it on many machines, you've got to buy many compilers. And that's annoying, right? You've got to buy a compiler for each machine. So what Java came out and did is they compile it in 2 steps. So we have Java. When you run it through the Java compiler, and you say Java C, and then your file name, X, Y, Z dot Java. The result is right. The result, the Java compiler creates. It does create zeros and ones, but it creates a class file like xyz.class. But this is code. This is like generic code, bytecode. That could make sense on any machine, but then there's a second step. When you run this on a particular machine, the machine has to, obviously in the end it's going to run on that particular machine's hardware. But if that machine has a Java virtual machine, then the output of the compiler, which is acceptable on any machine, gets converted into that particular machine's, something that particular machine's hardware can understand. So therefore, you could write Java code, run it through a Java compiler, and save this file. This file you can now mail out to any machine, as long as the machine receiving it has a Java virtual machine. And the Java virtual machine will take this quasi-compiled code and make it run on the particular machine you're on. And I haven't had this happen in a few years, but a couple of years ago, I'd go to a website, the website would send this code and say, the machine you're on doesn't have a Java virtual machine. Would you like to download it? I don't know if you've getting, I don't get them anymore. I think every machine in the world now has it. But for a while, though, you would be, for whatever architecture you're on, this code would try to run, and there's no Java virtual machine to interpret it to the machine you're on, the processor that you're on. So you could go out, it'll ask you, do you want to go out to Sun Microsystems, they invented Java. You want to go out to that website and get a copy of the virtual machine on your machine, and then that machine's good to go. So Java runs pretty much on every machine, because now every machine has the Java virtual machine on it. So now you can compile stuff. You don't have to worry. So there's really 2 steps. You're compiling and then running the class that you compiled. So the compiling step, the output of that, the class file, will run on any machine as long as the machine has the Java virtual machine, which maps those instructions to the architecture of the machine. And then C# copied that same concept. No, one sharp. C# is Microsoft's version of Java, I think. And so they copied that idea that you can go